Hello friends, in this video I am going to discuss second mean value theorem of differential calculus, Cauchy's mean value theorem. Let us first come to the statement. If two functions f and g defined on closed interval ab are first continuous on closed interval ab, second derivable on open interval ab, third g dash x is not equal to 0 for any x in the open interval ab, then there exists at least one real number c between a and b such that f of b minus f of a divided by g of b minus g of a is equal to f dash c by g dash c. Here we have two functions f and g instead of one function as was in Rolle's theorem and Lagrange's mean value theorem. Here we have two functions f and g such that they are continuous on closed interval ab, derivable on open interval ab, and g dash x is not equal to 0 for any x in the open interval ab, then there exists at least one real number c between a and b such that f of b minus f of a divided by g of b minus g of a is equal to f dash c by g dash c. This is Cauchy's mean value theorem. Let us prove this statement. Okay, let us prove this theorem. Here first we note that this g of b minus g of a is not equal to 0. Here we note that here we have g of b minus g of a is not equal to 0. Since if g of b minus g of a is equal to 0, if it is equal to 0, then as we know from the statement, gx is continuous on closed interval ab, derivable on open interval ab, and from this g of a is equal to g of b. Then the function gx will satisfy all the three conditions of Rolle's theorem. And from Rolle's theorem, we will have, from Rolle's theorem, we have, there exists at least one real number c in the open interval ab such that g dash c is equal to 0. This holds from Rolle's theorem, but this will contradict the third condition of Cauchy's mean value theorem. Therefore, this is a contradiction to the third statement. Okay, this is a contradiction to third statement of Cauchy's mean value theorem. Okay, therefore, g of b minus g of a is not equal to 0. Okay, this is not equal to 0. Okay, now we will define another function phi of x involving fx and gx. We will define a new function in order to prove this statement, Cauchy's mean value theorem. We will define a new function phi x in such a way that it will satisfy the conditions, all the three conditions of Rolle's theorem. Okay, now we define a new function phi x defined as fx plus a of gx, where a is a constant, to be determined such that phi of a is equal to phi of b. We have defined a new function involving fx and gx designed in such a way that it will satisfy all the three conditions of Rolle's theorem. A is a constant to be determined such that phi of a is equal to phi of b. Okay, clear? Now phi of a is equal to phi of b implies f of a plus a g of a is equal to f of b plus a g of b. It is clear? This implies a into g of a minus g of b is equal to f of b minus f of a. Okay, and from this we have a is equal to f of b minus f of a divided by g of a minus g of b. Okay, clear? This is my constant a. Okay, this can also be written as, taking minus common here, we get f of b minus f of a divided by g of b minus g of a. Okay. And this is well defined since g of b minus g of a is not equal to 0. This is well defined. Okay. A is equal to this. Mark this as equation number 1. Now, phi is defined as fx plus a of gx, a into g of x. Okay. Now, f and g are continuous in closed interval ab. Therefore, phi x will also be continuous on closed interval ab. And same way, fx and gx are derivable on open interval ab. Therefore, phi x will be derivable in the open interval ab. Okay, clear? Now, phi is continuous. Phi is continuous on closed interval ab, being the sum of two continuous function. Being the sum of two continuous function. Sum of two continuous function, clear? On closed interval ab. Same way, phi is derivable also. Phi is derivable on open interval ab, being the sum of two derivable functions. Being the sum of two derivable functions on open interval ab. And from our this condition, as we have defined a in such a way, this constant a in such a way, such that phi of a is equal to phi of b, all the three conditions of Rawls theorem are satisfied. Therefore, by Rawls theorem, there exists a, this is a symbol for there exists. There exists a real number c in open interval ab such that phi dash c is equal to 0. Clear? This is from Rawls theorem. Now, phi of x is equal to fx plus agx. Therefore, phi dash c will be f dash c plus a g dash c. Clear? Okay. Now, phi dash c is equal to 0 implies f dash c plus a g dash c is equal to 0. This implies a is equal to minus f dash c by g dash c. Now mark this as equation number 2. Now from 1 and 2 we get f of b minus f of a divided by g of b minus g of a minus outside is equal to minus of f dash c by g dash c. Minus sign will get cancelled out. That is, we have f of b minus f of a divided by g of b minus g of a is equal to f dash c by g dash c. This is Cauchy's mean value theorem. Okay, clear? Now, we have a corollary to this theorem. When g of x is equal to x, then Cauchy's mean value theorem CMVT reduces to Lagrange's mean value theorem. Lagrange's mean value theorem. Okay, if the second function gx is defined as equal to x, then our Cauchy's mean value theorem will reduce to Lagrange's mean value theorem. Okay, now gx is equal to x. Clearly, if this function is continuous on closed interval ab, derivable on open interval ab for any x. Basically, for any x, it is continuous also and derivable also. Okay, here we have gx is equal to x implies g dash x is equal to 1, which is non-zero for any x In open interval AB, it is continuous also and derivable also. And third condition is also satisfied here. We see that. Okay. Now, G of A is A and G of B is equal to B. Now, from the conclusion of CMVT, Cauchy's mean value theorem, we have f of b minus f of a divided by g of b minus g of a. This is nothing but equal to f of b minus f of a, and g of b is b minus g of a is equal to f dash c by g dash c. G dash c is nothing but 1. From here we get, okay, now this is nothing but this is Lagrange's mean value theorem. Okay, that means if the second function gx is equal to x, then Cauchy's mean value theorem will reduce to Lagrange's mean value theorem. Okay, clear? Now we come to second statement, or another form of the statement, CMVT, another form of Cauchy's mean value theorem. Okay, now another form of CMVT. If two functions f and g, defined on closed interval a plus h are such that first is continuous on closed interval ab, a and a plus h. Here b is replaced by a plus h. Second, derivable on open interval a and a plus h. And third, g dash x is not equal to 0 for any x in open interval a plus h. Then there exists one real number c in open interval 0, 1 such that f of a plus h minus f of a divided by g of a plus h minus g of a is equal to f dash a plus theta h divided by g dash a plus theta h. Okay, this is another form of Cauchy's mean value theorem. Here we have replaced b by a plus h and c by a plus theta h. Theta, there exists one real number, theta, not c, theta in the open interval 0, 1. Here we have replaced b by a plus h and c by a plus theta h. Okay, now this c lies between a and b. Therefore, we have this, clear? And from this I get, subtracting a, we get this, and on dividing by h we get this is equal to this is inequality becomes 0 less than theta less than 1. Therefore we have this theta belongs to open interval 0, 1. We have this condition. Okay, this is another form of Cauchy's mean value theorem. Okay, now we come to next, generalized mean value theorem. Okay, next we have generalized mean value theorem. Generalized mean value theorem. Here we have three functions, f, g and h. Okay, now first come to the statement of this theorem. If three functions f, g and h defined on closed interval AB are, here we have three functions. Okay, first is continuous. All the three functions are continuous on closed interval AB. Second, all three functions are derivable on open interval AB. Then there exists a real number C in the open interval AB such that we have this and this. Determinant of this is equal to 0. This is generalized mean value theorem. Here we have three functions f, g and h. Satisfying these two conditions, all the three functions are continuous on closed interval AB, derivable on open interval AB. Then there exists a real number C in the open interval AB such that this determinant is equal to 0. This is generalized mean value theorem. Okay. Now let us come to the proof of this theorem. Proof. Same here also, we will define a function. Consider the function. We will define a new function. Consider the function phi defined on closed interval AB defined by fx, gx, hx, f of a, g of a, h of a, f of b, g of b and h of b. Determinant of this. Okay. Now let us define a new function phi x in this form. Okay. Now this is equal to, on simplifying this we get this is equal to f of x into g of a, h of b minus h of a, g of b minus g of x is equal to f of a, h of b minus h of a, f of b plus hx, f of a, g of b minus g of a, f of b. Clear? On solving this, my phi x is of this form, not this. G of a, h of b, h of a, g of b. This is a constant. Again, this is a constant and this is also a constant. Okay. Therefore, I can write my phi x in this form. I can write my phi x in this form. I can write phi x as a fx plus b gx plus chx, where a, b and c are constants. Clear? I can write my phi in this form, phi x in this form. Okay. Now, since each of these three functions f, g and h are continuous on closed interval AB and phi x being the linear combination of continuous functions is a continuous function. Okay. Since each of three functions f, g and h are continuous on closed interval AB and derivable on open interval AB, phi being the linear combination of f, g and h is also continuous on closed interval AB and derivable on open interval AB. Clear? Phi being the linear combination of continuous functions, it is continuous and being the linear combination of derivable function, it is also a derivable function. Clear? Also, we note that also phi of A is equal to phi of B. Since when I replace x by A in the determinant of phi of x in the definition of phi of x, which is determinant, two rows will become identical. And here also, if I replace x by B in phi of x, then here also two rows become identical. That means value will be 0. Phi of A is equal to phi of B. It is clear? Since two rows become identical when x is equal to A or x is equal to B. That means phi of A is equal to phi of B. Okay, that means the function phi x satisfies all the three conditions of Rawls theorem. Phi satisfies all three conditions of Rawls theorem. Clear? On closed interval AB. Therefore, there exists a real number C in the open interval AB such that phi dash C is equal to 0 by Rawls theorem. Okay. Now, phi dash x is A into f dash x plus B into g dash x plus C into h dash x, which also can be written as this is f of A, g of A, h of A, f of B, g of B and h of B. Okay, this is my phi dash x. Now, phi dash C will be, now phi dash C is, therefore, phi dash C is equal to 0 will imply this. This is Cauchy's mean value theorem. Generalized mean value theorem. Okay, hence a proof where C belongs to open interval AB. Okay, this is the proof of generalized mean value theorem. Okay, we have two corollaries to this theorem. First is when h is a constant function, the above theorem reduces to Cauchy's mean value theorem. If my third function is a constant function, then above theorem reduces to Cauchy's mean value theorem. Okay. Now let hx is equal to k, a constant. Then h of A is equal to h of B is equal to k, and h dash C is equal to 0. Clear? Since hx is a constant function. The conclusion of above theorem, this takes the form, this is determinant f dash c, g dash c and h dash c will be 0. This is f of A, g of A, here we have k, and this is f of B, g of B, k is equal to 0. Now on solving this, simplifying this, I get this is equal to, this is f dash c, g dash c. Okay, this is f dash c into this k outside, g of A minus g of B minus g dash c, this here k outside, This is f of b minus f of a. F of b minus f of b is equal to 0. That means k will get cancelled out. This is f dash c g of a minus g of b is equal to g dash c into f of b, f of a minus f of b. Okay, clear? And this is equal to f dash c by g dash c is equal to f of b minus f of a by g of b minus g of a. Here also we are replacing this f of b minus f of a. This is equal to minus of f of b minus f of a, and this is also minus of g of b minus g of a. Minus minus will get cancelled out, and we are left with f dash c by g dash c is equal to this. This is nothing but Cauchy's mean value theorem. Okay, which is CMVT, Cauchy's mean value theorem. Okay, clear? Next corollary to this statement, this generalized mean value theorem is, next corollary, second, corollary 2, we have when gx is equal to x, this gx is x and hx is k constant, the above theorem reduces to, that is generalized mean value theorem, reduces to Lagrange's mean value theorem, LMVT. If we are defining two functions g and h as gx is equal to x and hx is equal to k, then this generalized mean value theorem will reduce to Lagrange's mean value theorem. Okay. Now here we have gx is equal to x. This means g of a is and g of b is equal to b and g dash x is equal to 1 for every x in the open interval ab. Okay. And hx is equal to k means h of a is k and h of b is also k and h dash x is equal to 0. Okay, clear? Now the conclusion of above theorem takes the form this is f dash c here. Here we have g dash c which is 1, h dash c which is 0, f of a, g of a is a here and h of a is k here. Then here we have f of b. Here we have f of b and here g of b is b and h of b is k here. Okay, it is equal to 0. Now on solving this is f dash c into this k outside. Here it is a minus b minus 1 into this k outside f of b minus f of a minus f of b is equal to 0. Okay. Now this k will get cancelled out and f dash c is equal to f of a minus f of b divided by a minus b, or f dash c is equal to f of b minus f of a divided by b minus a. Okay, this is Lagrange's mean value theorem. Okay, which is LMVT. Okay, means if we the two functions g and h are defined in such a way, gx is equal to x and hx is equal to k, then generalized mean value theorem will reduce to Lagrange's mean value theorem. Okay, now that's it for this video. In my next video, I'm going to discuss some problems on Cauchy's mean value theorem. Okay, if you have any queries or any suggestions, please write to me in comment box. Thank you.